Hi, welcome to my channel back, and I just took some time in between to hold up the next session for you. I'm very sorry for that because I was a bit busy with some other work in between. So herein, like I said, that I will be showing to you one particular exercise on ADC, and we had been learning the ADC section of CC3220SF, the basic design architecture of the ADC, and today we will start off with a hands-on. So those guys who have been waiting for ADC as a practical example and hands-on, this is the one for you. But today I have some more plans, like I would like to also upload some more videos concurrently with this, with the SPI and I2C, but I have made some changes in my schedule. That is, I thought that I would discuss the architecture about the DMA, the I2C, the ADC, sorry, the SPI and other peripherals, and then come back to the exercises. But I think that would be a very lengthy process, so we have a workaround for that. Rather, I would prefer to go for an exercise with ADC first. Okay, then on a separate video what I will do is I will punch on a description on DMA as well as the SPI and I2C, because DMA is something that really works around between your peripherals memory, I mean from memory to your peripheral, or from one memory location to another memory location, or from a peripheral to the memory. So mixing DMA with SPI or I2C or UART would be a good way, or even ADC would be a good way to put your hands on these things. And once we cover all the peripherals, or maybe most of the peripherals, then we will slowly move into some higher level of application of this processor, because these are only basic things which you can do with even simple processors. But the reason why why we go for this kind of SoC is obviously the internet connectivity. So after maybe one more session we can put a hands-on with Wi-Fi or MQTT application, or an HTTP REST API application. That will depend on what we select. So right now what we will do is we will go on for an ADC. So as I said, like for any kind of application which you want to test, simply just move to this particular SDK that you've downloaded. I have downloaded 4.10, so I will browse through this. At any point of time, if you need to refer to any documents, they are here. You can just refer to the release notes or SDK users guide, but I would prefer you to follow my sessions. They might be slow, but they will be very, very, very helpful for you. So let us find out the ADC example that we are planning to import. So we will always import the example, as I have done before also, into our workspace or the project explorer, which is on the left side. Okay, so here you can see that under TI drivers, as I said, that for any kind of peripherals we can write our own drivers, but it is not recommended. Please do not go for that, because it will involve a lot of test cases and boundary testings, specifically the boundary cases. So it's always preferable that you use a stable well established driver, for example the one that is given along with the TI drivers. So I always prefer using TI drivers. So you can include your TI drivers into your free RTOS or TI RTOS, whichever RTOS you're using. So here we already have an example, that is ADC single channel. So basically what this example will do is it will use the ADC driver which is already inbuilt to make a number of samples. Now if you remember from the previous chapter or the previous lesson, I told you that the total sampling time is around 20 microseconds, and in that time the channels are scanned, and there are a certain number of cycles which the processor takes to sample the channel, and then it converts it to the digital value. So here what it will do, it will take a number of samples. So maybe I'm not talking about that sample which is taken in one shot. it's like a continuous number of samples we will take, say 10 or 100 or 1000, so whatever it is, and we will print the value through the UART. So here what we will see is we will see the use of ADC as well as the UART. So both these peripherals will be utilized, and it will be good for you. Okay, now if you have a problem with the jumper settings on your booster pack, or if you are using several other kind of, maybe you're coming from some other exercise, so you might need to change your jumper settings on your launchpad board. So for that, please refer to this board.html file. It will give you the required jumper settings. Okay, now I showed you the last day that the ADC basically has 4 user channels. Actually it has 8 user channels, but 4 of them are for internal use, and the rest are for applications. So for the application part, you have channel 0, 2, 4 and 6. So what we will do, we will basically instantiate ADC 0 and ADC 1 as you can say two ADC objects. Okay, and alternatively we will collect data from the channels. So apart from this, there is nothing more that is written over here. One thing is important, that is which you should remember, is if whatever kind of a terminal viewer you are using, like I use HTerm, so if you're using putty or whatever, do follow these settings. Okay, like the baud rate should be 115200 and data bits 8, stop bits 1. So these settings must be done, otherwise the value will not come properly. Okay, so the output will be something like this, like the ADC 1 raw result, ADC 1 raw result, 2, 4, 6, 8, and converted result. It's like this. So basically, what is a raw value and what is an ADC converted value? This I will explain now. Wait. So if you remember the last day, I told you that for an ADC, basically what it does is it converts a voltage. This is an analog voltage, which is, say, if this is my time curve, and then this is my you can say the voltage curve. So with time, you can see the voltage is linearly rising. Okay, so if we present this in form of an equation, we can write that VA is directly proportional to T. Okay, so in this kind of a situation, or maybe the voltage need not be linearly rising, it can be, it can be coming from any kind of sensor. It can be something like this also, say any sensor value, with time the voltage is changing. So if we are going to sample this, if we need to sample this, so we need to, convert a part of this voltage into the digital domain. Suppose if we convert this part of the time, for example, I started my conversion here and I stopped, or rather I started my sampling and conversion here. This is my start. Okay, this is my start and this is my stop. So what basically we will have is these voltages. Suppose if I go for the red curve, okay, this voltage will have a certain digital value. For example, this may be say if the highest value, if I take over here, is, I'm sorry, if the highest value I take over here is, say, 1.5 volts. Okay, so approximately this would be something like 0.75 volts, and this would be half of that. So let me consider this something around say around 0.4 volts. Okay, so this is 0.4, and my end time, the voltage I get is, say, for example, 0.7 volt. So between this time, my voltage has risen from 0.4 to 0.7, right? So when the ADC will, take this value, the ADC will first convert it into a raw value. So if you have a look over here, you can see that the raw value is 230. For example, in this case, the raw value is 230. Now 230, what does that mean? It means that now remember, we have a 12-bit ADC. Okay, so what is the resolution? The resolution would be the maximum voltage divided by 2 to the power of 12. Okay, so this would come out to be something like 2 to the power of 12 would be I think 4096. Okay, I'll just convert it. Okay, so this is coming around 3.6 millivolts. Okay, so each and every digital value will be equal to 3.6 millivolts. So now for 0.4 volts, what should be the digital value? So naturally, if 3.6 millivolts is equal to, say, my ADC output raw value is 1, so for 1 millivolt it will be equal to 1 divided by 3.6 millivolts, so that is 0.0, as we have in the calculator over here, 000366. Okay, I am sorry, this is not 3.6, it is 0.36 millivolts. I am extremely sorry, this is not 3. I'll just correct this over here. It should be 0.36 millivolts. Okay, so 1 volt is equivalent to this much, so 0.4 volt will be equal to how much? Will be equal to 0.4 divided by this value, this one. Okay, so let me calculate how much it is. Okay, so it's coming out to be 1092. So if you convert this into raw value, it will be 1092. Okay, similarly the 0.7 volts maybe will be something double of this, and so just remember that whatever is your reference voltage, that is 1.5 volt, if 1.5 volt is your reference voltage, this should correspond to 4095. So obviously if 1.5 is should be giving you a raw value of 4095, the half of that, that is 0.7, will obviously be giving you something half of that, because this ADC is or will always give you a linear output. So 0.7 we can approximate to a value of around, say, you can take something as 2050. So basically these are your raw values. This is your raw value, this is your raw value. Now if you go back to the example, they have converted that into the microvolts. So what they have basically used is that the conversion that we have done, they have just reversed it back, and they have calculated that, okay, if 1092 is the output of the ADC, then obviously the voltage that I am measuring, or the system is measuring, is 0.4 volts. Obviously 0.4 volts will be 400 millivolts. This is nothing but 400 millivolts. And what is 400 millivolts? 400 millivolts is nothing but 400,000 microvolts. So that is how they are converting it, just for you to understand. So the raw details and the conversion details both are given. So I just gave you an example, just to have an idea of it, how it is happening. So let us now open the particular import the particular application and try to run it. Okay, so I have selected to import it. This question will be asked to you, so you can just select your target, and since I'm using CC3220SF, I have imported this. So as you can see over here, It is already imported. So let me first have a look of the sysconfig. Always remember that the system configuration modules or the modules that has been included, that needs to be first checked and inspected. So here what have been included, see, the first thing that has been included is display. Obviously this is a UART based display driver. As you can see that it is using the XDS UART and not the board UART. Okay, so this is something very important. Here you can change the baud rate if you want. If your system doesn't allow you to go beyond a particular value, you can change it to 9600, but we will keep it for 2115200. This is the UART buffer size, which is around 1024. So this is basically for the display configuration that we are using. You can change the name over here, but if you do change the name over here, I suggest that you also do it in the code. Now after that we will see how many ADCs. See, we have declared two ADC objects. So this is ADC object 1, this is ADC object 2. The ADC object 1 has been given a name, and the pin that it is using is obviously P59. Okay, so that is my header output pin. There are also other pins if you want to select, but the star ones, some header outputs are not connected. If you want, you can just refer to my first video, so be very careful about that. Okay, so they are using this P59 header for ADC 0. For ADC 1 configuration, they are using P60 header. Apart from this, we are using the power management module. This is just included. We do not need to understand what it is right now. Just we will have a detailed discussion on power management modules. So as of now, we are using the general sleep policy, the general initialization policy, and also for the other settings, let it be as it is. Okay, and apart from that, we are using the RTOS module, which is the TI RTOS. If you want, you can use the free RTOS. If you're using free RTOS, do select this. And so this is all that we have in the settings. And one thing more that we need is the UART, because for the display to be shown, we need a UART to be configured from the microcontroller point of view, because we are using the XDS UART to the PC, but the chip needs its own UART module or peripheral to be enabled and configured in order to read the data from the ADC and then transfer it to the XDS module. So for that, you have to select this UART. So here also you can see that we are using XDS UART. I mean, it'll internally fetch the value, convert the value, and transfer it to the XDS. So this is all that we need as of now, nothing much more. Okay, so the RxTX pin configurations are also given over here. You can have a look, just go through these files, like have a browse through them. Then we come to the first file, that is, as I said in my previous video also, the main TI RTOS. In main TI RTOS, what we are basically doing here is, it's very simple. We create two basic threads. Okay, in this main thread, I'll show you. This is our main thread. Okay, so for other initializations, you can refer to my previous video. We do the first board initializations, then we have to initialize the parameter structures, we have to give them memory buffers, and then we have to tell the thread that which particular type of a thread you want to create, whether it is a joinable or a detached thread. So you can just move on to the main thread. Now the main thread is here. So basically what we are creating is, we'll just have a very short look. We are creating two functions. One is thread function 0 and the other is thread function 1. And what are these two functions doing? It's very simple. ADC 0 will take 10. I will just show you over here. ADC 0 will give me one sample. I mean, it will measure one sample and it will send to the UART. Okay, and ADC1, that is ADC instance 1 or object 1, will take 10 samples and it will send to the UART. So this is the basic motive of the two thread functions. So I'm not going into the depth. You can just dive into it. As I also told you previously, as in the case of GPIO, we had initialized the GPIO inside the main thread. Here also we are initializing the ADC, we are initializing the display init for the UART. that is in order to send the data to the UART so that we can acquire it in our USB. Okay, so here you can just write whatever you want to display initially. Now after that, what we are doing is we have to spawn the threads. So here we create the 2 threads. Remember that we have already set the system that the threads will be of detached type. They are not joinable threads, so they are going to release the resources once they are over, once the threads have been once the functions have been cleared and the threads have been finished, the threads have finished their execution, it will release the resources. So we have already set that state as detached state. The thread stack size, that also we have declared over here. The thread stack size is 768. Remember, this has to be lesser than the main thread, which we have defined as I think 1024, otherwise there will be overflows. And apart from that, just we need to create the 2 threads. So one thread is here, thread function 0, and the other thread is here with thread function 1. Now both the threads will have same priority. As you can see, there has been no change in the priority. So once one thread will run, it'll fetch the ADC value for one sample, it'll transfer, it'll make a callback and transfer that. We will see how it is being handled. And in the second one, it'll fetch 10 values and it will be shown in the output. Okay, so now let us go into the thread functions. Okay, so here we have moved into the thread function 0. In the thread function 0, it is a one-shot conversion. It is written only over here. So basically the ADC will jump, the system will jump into the ADC. The ADC will measure the input and it'll show the value to the output. And in the second one, that is thread function 1, you have ADC sample count, which has been taken as 10, and accordingly, this for loop will execute. It will keep on executing. We have the ADC convert API, which will convert the values, and accordingly for each and every conversion you will be getting the data. Remember, one important thing is that whenever we are measuring or whenever we need to convert any value using ADC, we have to go for the ADC convert, and before ADC convert you have to go for ADC open. So there's a particular method in RTOS that you have to follow. I will just tell you in brief. That is, you have to first declare the parameters for an ADC. That is, the ADC handles. For example, I want to create 2 ADC objects, so each and every object will have its own handle. So whenever you initialize the ADC, that is over here, ADC params initialization, you basically allocate memory to the parameters, and after that when you open the ADC, okay, and which ADC you are opening here? Opening ADC object number 0, which you have configured in sysconfig. So you will have a handle for that, and that handle will be passed on to the value ADC of the data structured ADC handle. So basically it will give you an access to the ADC object 0. So whenever you want to convert any value about your for using your ADC, you have to follow this process. You have to open the ADC to get the handle. You have to then convert using the same handle. See the same handle has been passed, and in case if you get an error, you will get caught over here. And after you do all your conversions, whatever you want to do, you have to close the ADC. So the same procedure is also followed over here. Here we are converting only one value, here we are converting 10 values. So now what we will do is we will download the code, but one thing I cannot show you for this particular video is that I cannot show you the video of my launchpad board. So like I could not connect wires to any kind of potentiometer. What I would suggest you is that please follow this particular detail of wiring. Just hold on, I will show you. So basically what I wanted to tell you is that just take a 1.5 volt DC source. You can take a 1.2 volt rechargeable with AAA or AA battery or any other source you have, and you can put a 10K pot on it, and from the middle point or the variable wiper point connection of the pot, you can just connect the P59 pin of the launch pad. Similarly for another pot, make sure that both the pots have the same value. that is 10K or 20K or 5K, whichever you choose, and you can connect it to P60. So once you follow this connection, what will have is you can use your multimeter to measure the voltage over here. Suppose you measure the voltage over here and you measure it as say it is around 0.02 volts, okay, and for here it is around 0.08 volts, okay. So whenever you measure these two volts using your multimeter, you do convert them into the raw and the, or rather I would say just convert it into the raw values. Now what you can do is, now you download that code. So you can, I hope you can find out the particular pins in the launchpad. In case if you have any kind of issue, do mention in the comment. I will do this as a video and I will upload it to my channel, where I'm sure you will be able to do it yourself. It's not a big deal. The launchpad pins are over there. You have a 3.3 volt output in the launchpad, but I would recommend you to first don't go for 3.3 volt, go for a 1.5 volt battery. So for the 1.5 volt battery, positive terminal you have to connect to that to the variable resistor. I'm specifically saying this because there are many guys I know who are freshers. They will have a problem with this. For experienced people it's nothing. Maybe they will think that why am I saying all this, but for freshers I have got big things as questions for freshers. So if this is your 1.5 volt battery, okay, so you know this point will go and this point both will directly be connected to here. So this is your positive connection, or the plus sign of the battery. This is your higher potential side connection, and this sign which I have drawn, this will be connected basically to the negative terminal of the battery. Okay, so this is going to be connected like this, and also the same connection will go to the GND pin of your launch pad, because remember that if your ground is not common, your voltage will be floating and you will have erroneous values. So there have to be a common reference point, because unless and until you are standing on the first floor of a building, you can't say if the guy on the other side of the road is standing on the fourth floor of the building. No, you cannot, because you always need a reference, you always need a ground, you always need a stable measuring level to say which is at a higher level and which is at a lower. So that is why we have to connect the ground of the launch pad to the battery. So once you do that, next, after downloading, see the code has been downloaded. So after downloading the code, as I said in my previous video, you will see that you can find out from your device manager that which COM port is your XTS. Mine is COM3, so I will connect my COM3 and I will run my code. Okay, so okay, we have a lot of things out here. I'll just okay, so if we I'm not interested in the code much because I have already explained to you what is happening. What I will show you here is that, see, the conversion was started. Okay, now the raw result was 3, then the raw result 0 was 0, then ADC 0 conversion. So one, can you see one thing, that is ADC 0 function, that is thread 0 function, is getting spawned, or it is getting executed. Then ADC 1 function is getting executed over here. Okay, then again ADC 0 conversion is happening, then again ADC 1 conversion is happening. Okay, but right after ADC 1 conversion, ADC 1 raw result is being displayed. Okay, so it's very interesting that your ADC 0 is running over here, your ADC 0 is running over here. Okay, your ADC 0 is running over here, and then after that your ADC 0 isn't running at all. Why will it? Because your ADC 0 thread was spawned, it measured the raw value. This 3 is nothing but you can say it's a it's a kind of a floating value because I haven't connected the launchpad pin, so it is some floating voltage, leakage voltage, which it is measuring. So the thread was executed. After that, ADC1 thread was taken up. Okay, the processor swapped or switched the thread to ADC1, or rather I would say that the thread function 1 was taken up. So over there I will have to make 10 samples. So while it was being measured, or while raw result was being collected, ADC1 raw result procedure was started. And then when ADC conversion was finished, ADC0 conversion result came up. So 3 since it had some floating value of 3, it calculated and said, okay fine, your value 3 is nothing but 1074 microvolts, which means 1.074 millivolts. So after that, ADC0 had got nothing to do because ADC1 thread was still not yet complete. Over here my ADC0 was closed, as I showed you in the function. So after that, ADC1 thread was taken into action. Because ADC1 raw result was happening before, so here what I'm getting is the conversion result. ADC1 raw result was happening over here, so the thread started here, and then the thread was taken up over here. Okay, and then that thread continued till we had all the 10 results, that is 0 to 9. And then your system has gone to a halt mode. So this you have to understand that how the swapping has been done. And one thing that TI offers us is ROV, that is runtime overview. It's something that is very interesting. From view, I'll show you. In the runtime overview, you can see how your entire process or your entire function was executed. And this is very important because once you execute your code, you can have the exact thread type, how much frequency each thread has taken, how much time each thread was given. Like, you can also have system diagnostics. In the configuration file, you can also enable logging. And if we enable logging, in one of the examples we will do enable logging. So if we enable logging, then we can actually see in a time graph that how threads has been switched. For example, one thread was given up, suppose you had two threads of, say, priority 1 and priority 2. So one thread was taken up, it was finished, and then thread 2 was taken up, and then maybe thread 2 locked a mutex or a semaphore, blocked a semaphore, and then when it came back and thread 1 was given the chance to run, it got wait it had to wait because thread 2 locked a semaphore. So all these things really will see in the mutex and semaphore schemes, and that is where I will explain this ROV runtime object view. And there is also another ROV which gives you the exact graph functionality. So all these things we will see details when we will explore the kernel functionalities. So this, if you want, you can also explore yourself. You can directly connect with the core, and you can see that how your switching, your threads has been switched, and you can have a good overview of the entire system. Okay, so this is where we can just end this particular program, or if you want to rerun it, you can just reset it. Okay, so we have downloaded the code again, and this time what we will do is let us just change the number of ADC samplings to let's make it as 12. And here we will clear it, and okay, so we'll just press F8. Sorry. So here it is. ADC 0 function was executed, then here it was converted to 358 microvolts. You can see that the value is constantly changing because it's in floating condition. So this is exactly what happens in ADC. This is a very basic tutorial on ADC, I understand, but once we get through all the peripherals, we will take up even more complicated examples, and we will move ahead. So I think that is enough for this session right now. Next session I will do on I2C and SPI connectivities, and we will try to read some data from an I2C slave and also from an SPI slave, and also discuss the DMA with you, because DMA is something very important we need to address. And after completing the peripherals, I will move into the UIA, that is universal instrumentation. There's a lot of instrumentation tools that you can use for debugging, and also along with UIA, we will look into the kernel properties like the gating, the priority inversion, the mutex, the binary semaphore, how and why it can be used for resource locking as well as for synchronizations, counting semaphores, and all these things, all these details we will see it at a later stage. So I think this was quite helpful for you. Thank you very much. Do subscribe and like this channel if you find it interesting and helpful, and do please comment and let me know that what kind of change you might want in the sessions, or if there's anything that is missing. Okay, thank you very much. Bye bye.